Hey guys, it's Justin, and today you're looking at the aftermath of a broken rope. On accident, you say? No, I did this intentionally to see what it would look like and how we could modify the setup to make it safer. Here you can see the end of the rope that broke. Here's my setup. Now, I set up a piece of plywood so that if the rope broke in the way that I wasn't expecting, it wouldn't endanger the neighborhood. Now, at the end that I expect to break, I tied a bowline and wrapped it over that hook. I basically have a cheap polypropylene rope that I bought at a local hardware store hooked up to my 4-to-1 pulley system because I have it arranged as 4-to-1 so that I'm in no way in line with the rope once it breaks. At the pulley end, I tied a double fisherman's knot because that is supposed to be stronger than a bowline. Like the bowline knot will break before the double fisherman's knot. And there I have my pulley system attached to the tree. Now this rope actually turned out to be harder to break than I thought. It was rated at 100 pounds, and I thought I would be able to break it pretty easily with a 4-to-1, but it turns out that I couldn't. And so here I'm tying a prusik onto my main rope so that I can hook up a secondary pulley system, and that was also in a 4-to-1 configuration, which left me with a total 16-to-1 compound mechanical advantage. Now, while I was pulling the rope, I measured with my fish scale how much tension I was applying to the end of the secondary pulley system, and when the rope broke, I measured it at 65 pounds. Now, if I multiply that out, 65 times 16, I'm exerting over 1,000 pounds of force on the rope to get it to break. Now, the reason why a broken rope is so dangerous is because that 1,000 pounds that it took to break is also the force that it will exert on anything in the way as it starts traveling. So if you had your fingers in the way, it would rip them off. And you can see there's quite a bit of energy released when it breaks. Let's watch that again. Here it is from a different angle. Here I have stakes placed at 1-foot increments so that I can see how quickly the rope is traveling. This is the distance per frame. And we can see that I have my spreadsheet. I have a place for feet and inches, and then I convert that to decimal, and then I take the difference between each measurement, and then I average those, and I get an average of 1.39 feet. And then I figure out my frames per second, and then what that means as far as time per each frame, and it's 4.1 milliseconds. So I can calculate the feet per second, and then the miles per second, and then the miles per hour. So the rope end was traveling at 227 miles per hour. In case you're interested, this is what's left of the bowline knot. It completely disintegrated when the rope broke. Here is the double fisherman's knot. I don't think I'll ever be able to get that untied. Now, the way to make a rope safer is to dissipate that energy somehow, and the way that I'm going to do it is just simply by laying a sheet over the rope. And what this will do is reduce the ability of the rope to snap back because it will get tangled in the sheet. And because the sheet has a large surface area, it has air resistance which will slow it down as well. So you can see that the sheet is very effective at tangling with the rope. Now, if I had something metal at the end of the rope, I might have to have something with more mass to slow it down and dissipate that energy. Hey, do you like these videos? Subscribe. I'll make more. Bye.